Hi, I'll be presenting a theory of stabilization by skull carving by myself, Mathieu Lamarre, Patrick Anderson, and Étienne Danvoye from SEED, a research group at Electronic Arts. This work will be presented live in the technical communication track of SIGGRAPH Asia in December. What is facial animation stabilization? Our avatar likeness capture starts in the light stage with a multi-view camera setup. Many facial expression, combination of facial action units, are 3D scanned using multi-view stereo and photometry. Even with a professional quality chair with a headrest, the actor's head moves when performing expression. The head motion must be separated from the face deformation to create a controllable animation model. This process is called stabilization. Here are two important papers addressing stabilization. Beeler and Bradley presented rigid stabilization of facial expression at SIGGRAPH 10 years ago. It's a specific solution for a professional facial animation pipeline that uses an artist-created skull template. The skull is automatically deformed and registered to 3D scan using a custom energy minimization algorithm. It uses 8 manually placed points on the 3D scans and assumes skin thickness values at these points are constant for all people. It also uses a single constant weight map for skin thickness variation from motion. This is a limitation since medical literature shows that skin thickness varies between people and is correlated with the body mass index. Lee and colleagues' frame model presented at SIGGRAPH Asia 7 years ago is still very popular in research. It contains a linear blend skinning hierarchy with a joint for the skull. Therefore, it can be used for stabilization. The main issue with the flame model is that it has no skull-specific energy term during training. Therefore, some portion of the deformation fitting error is propagated to the skull pose. The inspiration for skull carving comes from two influential papers from the 90s. Laurentini introduced the shape from silhouette algorithm and the visual hull concept. The visual hull is the surface of the volume that explains all the silhouette of an object from different viewpoints. Koutoulas and Seat invented the space carving algorithm, in which the volume is gradually carved from the outside using a photoconsistency test. The isosurface of the carved volume is the photohull. By symmetry, we propose a volumetric skull carving algorithm performed in stabilized space. We name the surface of the intersection volume of stabilized scan the stable hull. Here is our method. The expression set that needs to be stabilized may contain between 10 and 100 scans. We first compute the axis-aligned bounding box over all expression 3D scan. A voxel array is defined in this box. For each scan, we determine whether each voxel is inside or outside the mesh using Barrels and colleague fast-winding numbers method from libIGL. Next, the sign distance are estimated by the fast-sweeping implementation of Vicini and colleagues. Voxel arrays are simple and fast SDF representation, but they take too much VRAM to stabilize hundreds of expressions. Therefore, we train a simple triplane MLP representation to compress each SDF. A triplane connected to a multi-layer perceptron with ReLU activation approximates the SDF well. This representation takes 6.4 megs for 0.2 mm mean absolute error. Before we can start skull carving, we need a good initialization for the rigid transforms. An upper face template mesh is aligned on each SDF using our mode per suite method, which we published in 2018. Skull carving is computed in a smaller bounding box defined by the upper face template on the neutral scan. Here on the left is the current stable hull. It's the isosurface of the maximum distance to the stabilized expression SDF, up to the expression shown on the right. In orange is the surface of the stable hull that was carved by that particular expression. In this case, the side of the cheek were carved. Let's look at the next expression. This is the first expression with visible teeth. We see the teeth are carved in the stable hull. Now let's look at the full process from the start. In practice, this process occurs in parallel on the GPU when the maximum over the expression dimension is computed. Our optimization energy is based on the hypothesis that a portion of the surface of the stable hull should align on the 3D scan surface of each expression. The justification is that when doing expression, muscle and other tissues move around. They can change thickness everywhere all at once. For example, raising eyebrows make the forehead thicker, but it exposes the brow ridge bone. We optimize all expression, rigid transformation, and stable hull shape simultaneously using PyTorch Adam implementation. The stable hull is computed with FlexiCube, a differentiable isosurface extraction method of Shen and colleagues. Here you can see the absolute distance to stabilize scan in pseudo-color between the start and now the end of the optimization. Here you can see the difference of the shape of the stable hull for the same optimization at the start and at the end. We can see that the shape changes are fairly subtle. The teeth and nose arch are better defined. Here we show the result using a split view with the stable hull on the left and a photoreal rendering on the right. The animation comes from simple interpolation between the shapes. The shoulders were pinned and the neck was fixed with a delta mush deformer to avoid distracting motion. Look at the teeth, nose, and forehead region to see that these shapes are well stabilized. See how the thickness of the skin on the nose changes. For 32 diversely sampled persons, we created a set of 227 expression scans with visible upper teeth. We manually classified stabilization errors in the 3D software using the Move tool. We aligned an upper teeth model on the stabilized expression scan. Then we estimated the worst-case translation error per person and sorted this value between error brackets. The result showed that skull carving outperforms other methods. Limitation. Skull carving needs another method for initialization. It doesn't converge from the initial scans alone. On current 24 or 48 gig GPUs, it's limited to 50 or 100 expression. So it's not adapted for 4D tracking stabilization, where we may have way more than 100 frames to stabilize. As future direction, we want to learn a stable subspace, perhaps with a mesh autoencoder to improve convergence. We also would like to train a head-to-stable hull model for fast initialization. Finally, we would like to fit an upper teeth model on the stable hull. That concludes the presentation. Thank you for listening.